Okay, this is a pendulum problem. So even though the force of gravity is constant, the relationship in this problem between the force of gravity and the displacement, the angle between those two, is going to be changing throughout the problem. Therefore, we have to use work energy because the acceleration is not going to be constant. So let's start with a picture of the pendulum. So here's the pendulum at its lowest point. And at that lowest point, the child is moving with a speed of 4.5 meters per second. And the pendulum has a length of 3.3 meters. And we want to know what maximum height h does the child reach. So the child is going to swing up to this point, which is some height h above the initial point. It's going to make some angle theta here with the vertical. Alright. Wow, so let's see. To do work energy, we need to identify the forces in the problem. So the forces acting on the pendulum are gravity and tension. And that's it. There aren't any other forces in the problem. There's no applied force. I mean, yes, the child starts with an initial speed of 4.5 meters per second. Maybe she was pushed or whatever, but our analysis begins after she has that initial velocity. So we're not worried about what force gave her that initial velocity. So it really is true that the only forces doing any work in this problem are tension and gravity. And the work done by tension in this problem is zero, because at every point in the motion, the force of tension is always perpendicular to the displacement, right? No matter where you look. If you look down here at the bottom, the force of tension points up, and the displacement is to the right, so they make a right angle. Over here, the displacement goes back that way, and so the force of tension and the displacement make a right angle. Everywhere in the motion, the tension is perpendicular to the displacement, and so the angle between them is 90 degrees, so the tension force does not do any work. Gravity does, it always does mgh worth of work. In this case, it does negative work because it goes up. If you want the details of that, I guess, we could say that the initial potential energy is 0, and the final potential energy up here is mgh, right? And so if you take minus the change of potential energy associated with gravity, that's minus uf, minus ui, which is minus mgh. So that's where that comes from. Alright, well, that's it. We've calculated the work done by each force in the problem, so now we set up the work energy theorem. We say the work done by tension plus the work done by gravity is equal to the change in kinetic energy. So minus mgh is equal to 0 minus 1/2 mv0 squared. Now, the kf is 0 at max height. The child reaches the maximum height, and so the final velocity at that point is 0. The final velocity of the pendulum is 0 at that point, and so we're left with minus mgh is equal to minus 1/2 mv0 squared. The m cancels, fortunately, and so I get 9.8h is equal to minus 1/2 times 4.5 squared, and h is equal to 1.0 meters. So there's the maximum height reached by the child. That's part A. Part B, what angle does the swing make with the vertical at that point? Well, let's go back to our diagram. The 3.3 meters is equal to the length here. I want to note here that the length of this side here is also 3.3 meters, right? The pendulum is 3.3 meters, whether or not it makes an angle with the horizontal. But if I look at this triangle here, so let me denote another triangle. Okay, the hypotenuse of that triangle is 3.3, and this adjacent side is 3.3 cosine theta. Okay, and so that means that that h plus 3.3 cosine theta has to add up to 3.3. Okay, so h is equal to the length of the pendulum minus the length times cosine theta. Well, I've solved from the last part that h is 1.03 meters, if I maintain all of my precision here. And so, if I go through and I solve this for theta, I get 0.687 is equal to cosine theta, and so theta is equal to 47 degrees. Right. Part C. Now we have there are frictional forces, and the child only rises to a height that is 85% of your answer for part A. Okay, so the final height is 85% of 1.03, which is 0.8755 meters. So we want to know how much work is done by friction. Well, right, remember there are three ways to calculate work. There's, we have the work done by a force is equal to the magnitude of the force times the magnitude of the displacement times cosine theta. I can't use that here because we have no idea what the frictional force is. We don't know what the displacement is either, to be honest. So that's completely out. The second way to find the work done by a force is to use change of potential energy associated with the force. But friction doesn't have potential energy associated with it. And the third way is what we're going to do. So for this problem, I know that the work done by tension is still 0. The work done by gravity is minus mgh, but we have to use our new height. So minus the mass, which is 25 kilograms, and height, so that's minus 214.5. Okay, and then the work done by kinetic friction is going to be our unknown. So the work energy theorem says that the sum of the works is equal to the change in kinetic energy. Again, the final kinetic energy is 0, and so I get 0 minus 214.5 plus this unknown work done by kinetic friction is equal to 253.1. So the work done by kinetic friction is therefore minus 38.6 joules, which I've got to round off to minus 39 joules. There's our answer to part C.